We hear statistics all the time, like 40% of people skip breakfast, or this new tire lasts 50,000 miles. But think about that for a second. How can researchers possibly make those claims without interviewing every single person on Earth? The truth is, tracking down every individual, what statisticians call a census, is almost always a logistical nightmare. It burns through massive amounts of time and millions of dollars. But the ultimate barrier to a census is something called destructive testing. Imagine you run a factory and need to verify exactly how much pressure your new tires can take. If you ran a census and tested every single tire until it popped, you'd know their limits perfectly, but you'd also have zero inventory left to sell. Because studying an entire population is usually impossible, science relies on selecting a tiny, manageable fraction of items. We use that small group to mathematically predict the reality of the whole. But pulling a small group to represent everyone carries a massive risk. If researchers are blind to their own biases, a sample can spectacularly backfire. Take the 1936 United States presidential election. The Literary Digest magazine set out to predict the winner between Alf Landon and Franklin D. Roosevelt. They launched a survey of enormous scale, mailing out millions of questionnaires. To build their mailing list, they pulled addresses from telephone directories and car registration records. The magazine confidently predicted a massive victory for Landon. Instead, FDR won overwhelmingly. The pollsters missed a crucial demographic detail. It was 1936, the middle of the Great Depression. Only wealthier Americans owned cars or telephones, meaning the magazine entirely excluded the working class from their data. Statisticians call this a sample frame error. It proves a vital rule. If the initial list of people you choose to survey doesn't exactly mirror the diverse makeup of your target population, every calculation you do afterward is completely useless. This diagram outlines two main philosophies for building samples. You have probability sampling, dictated by math, and non-probability sampling, relying on human judgment. On the probability side, every individual is given an equal, mathematically calculated chance of selection. This math physically removes human bias. But true randomness has limits. Imagine you need to survey a highly diverse city. A completely random draw might accidentally skip over smaller minority groups entirely, skewing your results. To fix this, researchers use stratified sampling. First, they divide the population into distinct socioeconomic or ethnic subgroups. Then they randomly pull equal proportions from within those specific groups, guaranteeing everyone is represented. Logistics present another hurdle. If you need to survey a massive, sprawling state, physically driving to randomly selected houses scattered hundreds of miles apart is way too expensive. The workaround is cluster sampling. You divide the state into regional units, randomly select just 3 or 4 of those regions, and then interview absolutely everyone living inside those selected borders. These probability techniques act as clever logistical hacks. They let researchers capture the accurate mathematical structure of a massive population without having to measure every single inch of it. Sometimes, though, mathematical randomness is impossible. When a target population is incredibly rare or hidden from public records, you can't build a random list. That is where you use a non-probability technique, like snowball sampling. Say you are trying to survey deep-sea scuba divers. You find just one diver, and you rely on that individual to introduce you to their specific network of friends. The sample grows organically from that single point of contact. But here is the hard truth of statistics. Even with a flawless strategy, natural variation guarantees that a sample's average will almost never precisely match the total population's true average. We call this sampling error. Because sampling error is a permanent, unavoidable reality, the field of statistics is never about achieving absolute certainty. It is purely the science of managing and quantifying uncertainty. If every single sample is guaranteed to have a margin of natural error, how can we actually trust any scientific study? We can trust the data because of the ultimate statistical law that saves the entire discipline, the Central Limit Theorem. This chart shows the Central Limit Theorem. The top row displays original populations with chaotic shapes. Now look at the bottom row. Pulling multiple samples, each with at least 30 subjects, creates something incredible. The averages perfectly organize into a smooth, symmetrical bell curve. While individual data points are highly erratic, the mathematical average of a large enough group always follows this unbreakable, predictable law of nature. You can think of all this abstract math like checking a massive, boiling pot of stew to see if it needs more salt. As long as you stir the pot thoroughly, which is your proper sampling methodology, eliminating bias, and you use a large enough spoon to clear that sample size of 30, you never need to consume the entire pot to find out how it tastes. A single, well-chosen spoonful contains the exact same reality as the whole.